Remember polyatomic ions? Let's see how this changes balancing equations. So when we're balancing equations that include polyatomic ions, we probably want to take a moment to remind ourselves what the heck polyatomic ions are. Remember, poly means many, atomic means atoms, so a polyatomic ion is an ion that's made of multiple atoms. So nitrate is an example, NO3. Carbonate, CO3 is another example. Hydroxide, OH, ammonium, NH4. Notice that these are all formulas that contain polyatomic ions. We can actually use an easy trick when balancing equations where polyatomic ions remain intact, stay together throughout the entire chemical reaction. So let's look at sodium nitrate plus calcium hydroxide. They're going to react in a double replacement reaction to form calcium nitrate plus sodium hydroxide. Now, I want to go ahead and count my atoms here, first step that I do in all of my problems. But I want to notice that I have polyatomic ions that are remaining as units. Like they're staying together on both sides of the equation. So when I lay out what I'm going to use to count my atoms, I'm actually going to count polyatomic ions as their units. So NO3, I'm going to count as one thing. OH, I'm going to count as one thing, and I'm going to use the parentheses to help me. So I have one sodium, one nitrate, because I could put the invisible one outside of the parentheses, one calcium, and two hydroxides on my reactant side. One sodium, two nitrates, one calcium, one hydroxide, or one OH on my product side. Right? If there's no parentheses around the polyatomic ion, I know that I only have one. Now I'm going to follow the normal rules of balancing. I'm going to look to see where things are unbalanced, and I'm going to try and balance them. I'm going to quickly show you guys how you could use the drawing method for these problems as well. So notice as I'm drawing, I'm including like one particle as my polyatomic ion. So I wrote OH inside the circle. I wrote NO3 inside the circle. Now, I want to get my nitrates balanced. So on the reactant side, I'm going to multiply 1 by 2, putting a 2 in front of NaNO3. So I'm going to have 2 sodiums, 2 nitrates. Now I've balanced nitrate. I still need to balance sodium on the product side. So 1 times 2 is 2. So I'm putting a 2 in front of NaOH. That's also multiplying OH times 2. And now I'm balanced. Notice I'm not worrying about multiplying the subscript outside of the parentheses over the atoms inside the parentheses, right? I'm not counting individual nitrogen or oxygen or hydrogen atoms. I'm counting the polyatomic ions as one formula unit. We'll do some more practice, don't worry. Let's do one more balancing equations with a polyatomic ion. So again, we're looking for formulas that contain these groups of atoms in an ion that stay together in the same ratio before and after the reaction. So in this example, we're going to have 3 polyatomic ions, nitrate, NO3, starting off in the compound iron nitrate, FeNO3, ammonium, NH4, is another polyatomic ion, and sulfate, SO4, is another polyatomic ion. So we have FeNO3 plus NH4 SO4 reacting to form FeSO4 plus NH4NO3. So it's iron nitrate plus ammonium sulfate reacting to form iron sulfate plus ammonium nitrate, another double replacement reaction. I'm going to start by listing my atoms or polyatomic ions so that I can count them. So iron, I'm going to list NO3 nitrate as one thing. I'm going to list NH4 ammonium as one thing. I'm going to list SO4 sulfate as one thing because those atoms stay together in clumps on both sides of the equation. So I'm going to list my ions on the product side as well, and now I'm going to count. So on my reactant side, I've got 1 iron, 2 nitrates, 2 ammoniums, and 1 sulfate. Products, 1 iron, 1 nitrate, 1 ammonium, 1 sulfate. And now it's just the normal rules of balancing, right? I'm going to remind myself that if I don't have parentheses around my polyatomic ion, that means I have an invisible 1. I've got 1 of that polyatomic ion, right? That's kind of what's tricky here. We don't want to mix up and say that we have 4 SO4s because of that 4 there. So to balance my nitrate, I'm going to multiply NO3 times 2 on the product side, which means I'm going to be putting a 2 in front of NH4, NO3. So I'm also going to be multiplying ammonium by 2. And it turns out that's actually all I need to do to balance this equation, right, is put a 2 in front of NH4, NO3. And now I'm balanced. So again, really look for these polyatomic ions. If they stay the same before and after, you can treat them as one counting unit. All right, let's do another balancing equations with a polyatomic ion practice. This is very exciting. So we've got practice number 2. We're going to look at aluminum oxide. So it's going to be Al2O3 reacting with sodium phosphate. So this is going to be a double replacement reaction. Most of these polyatomic ion problems are either double or single replacement problems. And so we're going to end up with sodium oxide, Na2O, and aluminum phosphate. So the first thing we're going to do is count our particles. We've got aluminum, oxygen, sodium, and we're going to count phosphate, PO4, as one thing. So aluminum, oxygen, sodium, and phosphate. So I have 2 aluminums on my reactant side, 3 oxygens, and 3 sodiums. I have 1 phosphate on my reactant side. I can think of those parentheses there. On my product side, I have 1 aluminum, 1 oxygen, 2 sodiums, and 1 phosphate. Now I need to start my balancing. I'm going to start with the one that looks the hardest to balance. So I see sodium, I see 3 and 2. We think about wanting to find the least common multiple when we see 3 and 2 like that. So 3 times 2 is 6, 2 times 3 is 6. Let me go put my coefficients in. So I'm going to put a 3 in front of Na2O because that's where sodium is found in the product side. That means I'm also multiplying oxygen by 3. I'm going to put a 2 in front of Na3PO4, which means I'm also multiplying the number of phosphate particles by 2. Whole phosphate, PO4, as like one thing. Putting a 2 in front of Na3PO41, right, the one outside the parentheses, I now have 2 PO4s. I am not counting the total number of oxygens or the total number of phosphoruses. I'm counting PO4 as its own unit. Now I want to look to balance aluminum and I want to look to balance phosphate because oxygen and sodium are both balanced. So I need to want to think about how to make 1 equal 2. So 1 times 2 gives me 2. So I'm going to multiply aluminum and phosphate by 2 and put a 2 in front of AlPO4 on the product side. Now I'm balanced. I can put a 1 in front of Al2O3 on the reactant side, and I have 2 phosphates on both sides, 6 sodiums, 3 oxygens, and 2 aluminums. The tricky part of these problems is remembering what the polyatomic ion is really made out of, right? So in this case, PO4, that's the polyatomic ion. So I'm not counting like 4 oxygens, 1 phosphate, right? I'm counting the whole thing as one particle. So this is how I would write the final fully balanced equation. 1 Al2O3 plus 2 Na3PO4 reacts to form 3 Na2O plus 2 AlPO4. For more practice, check out the other videos I've made with polyatomic ions and balancing.